Hi, my name is Iliashenko, and I will demonstrate how to speed up the secure comparison of encrypted integers. This is a joint work with Vincent Zucca. Our data is kept in the cloud. Banks outsource customers' data to the cloud providers to avoid deployment of necessary IT infrastructure for data storage. Due to the same reason, hospitals can use the cloud to store the medical data of their patients, thus sparing some money. Of course, financial and medical data is very sensitive and should be protected even from the cloud provider, which can be done by using encryption algorithms. Then the question arises how to work with encrypted data in the cloud. For example, how to get statistics about customers or patients, but at the same time keep all the data oblivious to the cloud. It seems contradictory as ciphertexts do not leak any information and the cloud needs to decrypt it first before going to computations. In 1978, Rivest, Adleman and Dertozes suggested the following hypothetical solution. What if the cloud computes on ciphertext such that a desired function is computed on underlying plaintexts without decryption? After computation, the cloud provider can just send only encrypted results back to the data owner. The encryption algorithm used in this protocol is called homomorphic. More precisely, homomorphic encryption is an encryption scheme that allows computations on encrypted data without decryption. The most advanced type of homomorphic encryption is fully homomorphic encryption that can compute any computable function on encrypted data. But there is also a somewhat homomorphic encryption that can compute any arithmetic circuit of bounded depth. In practice, somewhat homomorphic encryption is more efficient than fully homomorphic encryption. In this work, we focus on this type of homomorphic encryption. The existing HE schemes natively support evaluation of arithmetic circuits. In other words, they can compute polynomials. But many practically useful functions are not arithmetic, so they should be somehow approximated to polynomials of reasonable degree. In this work, we focus on comparison functions such as logical predicates is equal, is less than, and maximum-minimum functions. We will show how to speed up evaluation of such functions. To study the computation complexity of homomorphic computation, we should take into account which operations are cheap and which are expensive. Since there are two types of input in homomorphic encryption, plaintext and ciphertext, the arithmetic operations have two versions, namely with a plaintext and a ciphertext, or with two ciphertexts. The most expensive operation is ciphertext-ciphertext multiplication. It implies that when we evaluate a polynomial whose coefficients are public, that is plaintexts, we should pay attention to the number of non-scalar multiplications, where ciphertexts are involved. Multiplications by scalars are cheap. It is also important to remember that the encryption parameters of somewhat homomorphic encryption schemes grow with non-scalar multiplicative depth. This is why we aim to minimize this depth as much as possible. Let us provide more details on somewhat homomorphic encryption schemes we are going to use. There are three main types of HE schemes. The first type is suitable for bitwise arithmetic and includes FHEW and TFHE. The second type is efficient for integer arithmetic. The most well-known schemes of this type are BGV and BFV. And the third and the youngest type is suitable for approximate or fixed point arithmetic. At the moment it contains only one scheme called CTKS or HIAN. In this work we will focus on the second type that can evaluate arithmetic circuits and encode data into finite fields. The plaintext space in such schemes is typically a vector space over a finite field. Plus, there are homomorphic operations that allow to add and multiply plaintext vectors coefficient-wise and also rotate them, or select a certain coordinate and zeroize the rest. To compare integers homomorphically, we need first to encode them into the plaintext space. First, we decompose a given integer a into its base p prime representation. Every digit of this decomposition is also an element of the prime finite field fp. Then, every group of d digits can be mapped to an element of the finite field fp to d. And this means that we can convert the decomposition vector of a in base p prime to the vector of elements over fp to d. Note that this conversion is invertible. To compute integer comparison, we need the equality function over fp, which is defined in the following way and can be computed in a logarithmic number of non-scalar multiplications. Using the equality function, we can interpolate any function over a finite field using the Lagrange interpolation. The resulting polynomial will be unique and of degree at most p-1 in each variable. As a result, we have all the ingredients to compare encrypted integers. We use the fastest algorithm in the literature from Tan et al. The input of this algorithm is two integers x and y encoded as vectors of the finite field fp to d. The first step is to extract the digits of these integers, namely the elements of the prime field fp. This step is relatively cheap. Note that each output ciphertext contains the ith coefficients of all the coordinates of the input vectors. In the second step, the corresponding pairs of digits are compared with the equality function. Note that one homomorphic evaluation of the equality function compares L pairs of digits simultaneously. In the first step, similarly, the corresponding pairs of digits are compared with the less than function that returns 1 if the left argument is smaller than the right one, and 0 otherwise. Finally, the results of the equality and the less than functions on digits are combined by the lexicographical order. First, we compute the lexicographical order per each block of d digits, and then combine the results in the final lexicographical order equation that gives us 1 if x is smaller than y and 0 otherwise. So what are our contributions to this algorithm? Notice that the core part of the algorithm is the less than function over the prime field fp. In the existing literature, this function is the slowest one in the pipeline, so how can we evaluate it more efficiently? So the first method assumes that x and y are integers between 0 and p-1. Then the less than function is defined by the following lookup table, which contains only ones over its main diagonal and zeros anywhere else. We can use the Lagrange interpolation to find a polynomial of this function, which will be of this form. Tan et al. Showed in their paper that this polynomial can be computed in 3 p-5 non-scalar multiplications. Another method assumes that input integers are in the interval from 0 to p over 2 and p is a knot prime. In this case, the less than function is reduced to the is negative function that checks whether the difference between the input values is negative. This function has the following lookup table. Again, using the Lagrange interpolation, we can find a polynomial for this function. This method is called univariate because in fact we interpolate a univariate function. It was shown that such function can be computed in about the square root of 2p minus 2 non-scalar multiplications. Let's go back to the bivariate method, which has the following form. We proved that after expansion, many coefficients of this polynomial cancel out, such that the total degree becomes p instead of expected 2p-2. In addition, this polynomial always satisfies the following equality that simplifies its evaluation. And as a result, we can compute the less than function with 2p-6 non-scalar multiplications and improve the complexity given by the prior work. We also found that the univariate interpolation of the less than function has interesting structural properties. First, it can be represented as the sum of two polynomials, where the first one is the exponent of the difference of two inputs, and the second is the product of the difference with a polynomial of degree p-3 over 2, evaluated at the square of the input difference. As a result, less non-scalar multiplications are needed to evaluate the less than function by a factor square root of 2 in comparison to the prior work. An interesting detail is that the leading term of the interpolation polynomial can be reused to compute the equality function almost for free. And as a result, we can save a significant number of non-scalar multiplications while evaluating the lexicographical order. We can apply our observations to the minimum-maximum functions that can be easily obtained from the less than function. If we use the univariate method, then the minimum function will look like this. This saves one multiplicative level, as the complexity and the depth of the minimum function is the same as of the less than function. Plus, we can compute the ReLU function, which is very popular in machine learning. We tested our faster circuits in two applications. The first one is sorting, where you are given an array of integers and the goal is to sort them. We used the algorithm of Chetin et al., which has the minimum multiplicative depth. Let us illustrate it on a simple example where the input array has 4 integers. Step 1 of the algorithm is to compute the comparison matrix that contains the results of the less than function computed on any pair of elements from the input array. We can make certain shortcuts while creating this matrix. For example, each element on the main diagonal of this matrix is always 0. And also, with relation to the main diagonal, this matrix is anti-symmetric. So you can look at, for example, this term is 0, and its symmetric term with relation to the main diagonal is equal to 1. As a result, we need only n times n minus 1 over 2 homomorphic comparisons in order to compute this matrix. And these comparisons can be performed in parallel. Then we sum the rows of this matrix and obtain an array M. This array contains the positions of the elements of the input array A in its sorted version. In the second step, we create a new array by homomorphically selecting entries of A using the information from the array M. The selection uses the fact that this product of the equality function and an element aj is equal to aj if and only if the position of aj in the sorted array is equal to I. And the position of the element aj in the sorted array is already encoded in the element mj. Otherwise, this product will be 0. As a result, we can homomorphically compute the ith element of the sorted array. You can check that this algorithm returns the following array, which is indeed the sorted version of the input array A. Another application of our circuits is the minimum-maximum element of an array. To compute the minimum element, we could use the sorting algorithm, but this requires a quadratic number of comparisons in the number of elements. Another way is to perform n-1 successive pairwise comparisons using the tournament method, but in this case the depth will be practically big. As a result, we proposed a hybrid method by mixing two strategies. First, we perform t stages of the tournament method that outputs an array of a smaller size containing the minimum element, and then we extract the minimal element using the sorting algorithm. But now we need to sort less elements. As a result, the complexity of this approach is n minus n prime pairwise minimum functions and n prime times n prime minus 1 over 2 less than functions. We implemented the presented algorithms, including the prior work in Équipe, which is a homomorphic encryption library realizing the BGV scheme. For the experiments, we used an average laptop. We compared the performance of both our circuits of the less than function with the prior work of Tan et al. In this graph, you can see the speed-up factors of each of our circuits depending on the plaintext modulus p. It's easy to see that the speed-up factor of our bivariate circuit is almost constant and fluctuates around 1.5 as predicted by theory. The speed-up factors of the univariate circuit is increasing with the modulus p. The best running time that we could achieve is with the plaintext modulus of 131. The total time is around 16 seconds, but it is possible to encode several integers into one ciphertext and process them in parallel such that the amortized running time per integer is reduced. We obtained 11 milliseconds per integer, while the prior algorithm could achieve only 36 milliseconds. This is an improvement by a factor of more than 3. We also sorted 32-bit integers and compared our results with the best work in this area by Chetin et al. For any array length up to 64, our algorithm is faster. We also ran the minimum element algorithm on an array of the same length as in sorting. Here you can see the results for 32-bit integers. In comparison to other HE schemes, our work is one of the fastest with relation to amortized time per integer. Note that it was believed that the BGV-BFV schemes are inherently slower for comparison operations than the TFHE-like schemes. Our work demonstrates that they have almost the same performance. To conclude, I sum up the main contributions of this work. First, we fully describe the comparison functions over finite fields. Then, as a result, we designed faster circuits for these functions that allowed us to improve the running time by a factor of 3. The corresponding speedup is shown in 2 applications, sorting and array minimum maximum. Finally, our circuits show that the BGV scheme is also suitable for integer comparison and can be as fast as TFHE and even better than the CKKS scheme. Our future work will be focused on looking for other useful functions over rings and fields with efficient homomorphic circuits. Thank you very much, and please ask questions.